Good evening. So this is my second video of my series for the Physics Fireside Chats. I'm Clifford Chafin again, and I guess I'll say a little bit about myself, which I didn't say before, was I do have a PhD in physics from NC State. I did not choose to pursue a career in academia for a variety of reasons. One of which is that the job options are pretty poor. I didn't really enjoy my experience with reviewers. None of these are really unusual comments. It'll come up now and then, but also the price of publication is exorbitant. Some $2,000 or $3,000 sometimes for an article. It just didn't look like a good angle. So instead I got married, started a family. But I was always very passionate about my work. And so I've looked for an outlet for it beyond just putting things on the archive or ResearchGate. So I'll tell you about the kinds of problems I'm interested in. So what this isn't going to be, just quickly, is it's not going to be one of those beautiful, slick channels where they present established problems and do a beautiful job presenting them. I love those channels, like Brown Blue, some of those. These are really going to be topics that might be a bit controversial, but they're ones I've worked on for a long time. And I personally will tell you my love is on things like paradoxes, like electromagnetism, and I've dug these up in hydrodynamics and a number of other places. And I feel like I have something unique to say about them now. So I have not pursued publishing very hard because of the financial burden on my family and myself. But I'm still networking and talking about these ideas and hoping this will stir up some more conversation. Today, I'm going to be talking about diffusion. There is a long-standing problem in diffusion, whether of heat or of constituents, material, particles. The diffusion equations as they stand are not causal. And so let me actually get you to Fick's first law. So let me just throw up Wikipedia's article. And the current is proportional to the gradient of the temperature or the concentration, one of these. And from this, you can quickly derive a differential equation that is Fick's law. Let me just pull it up. There we go. So boy, doesn't that look like the usual diffusion equation? Looks very much like the Schrödinger equation. First order in time looks pretty parabolic. So we know these equations don't give causal results. So there have been a number of attempts to solve this problem. I mean, and if you're wondering what that means specifically, I make myself a little packet with compact support, and I release it and evolve it, and the packet spreads out, and it reaches infinity instantaneously. So there is no natural velocity of propagation as there is for hyperbolic differential equations. So there have been a number of attempts to resolve this. There are the relativistic heat conduction equations, hyperbolic heat equations, by Cataneo and a number of people. They seem like a logical choice to establish causality, but the problem with them is they introduced extra hidden degrees of freedom. So, I mean, it's a little bit like if you've ever studied the radiation reaction problem, you might find you get these extraneous solutions if you're not careful, things that just run away to infinity. The truth is, your initial data is purely first order. You specify the initial distribution of heat or concentration, and you evolve from there. So you get the second order, you need another derivative, and you don't have that. that's just one of a number of problems that pop up with this approach. I won't belabor it. Talked about it enough in life. But people do use it. They need it. Like when they're looking for solutions to simulations for very hot objects, very highly energetic plasmas, things like that. It's a relevant thing. So this work I did dovetailed with some work I was doing with hydrodynamics and a number of topics, some paradoxes that arise also in acoustics and surface gravity waves. And this is the first talk that's going to lead into some solutions in that area. Now, what I'd like to point out is, let's just consider a very, very basic case. So this is an article that's on ResearchGate. It's also on the archive. Essential infinite order, non-PDE behavior and continuum mechanics, and for hydro and diffusion. So I'm just going to be talking about diffusion today, and I'm just going to scroll through this instead of popping up a bunch of PowerPoints. So this is just a one-dimensional diffusion model. So it's meant to be really basic. I just have a chain of things. The things all move with some characteristic velocity v, and they move right and they move left. Then they make a random choice as to whether they're going to keep going right or keep going left. So if I start a distribution like this, it's pretty clear that the support of the distribution is going to stay finite, and the edge is going to move out at the velocity v, the characteristic velocity of the constituents. It feels very much like a simple gas model. So given that we just saw Fick's law derived or mentioned on Wikipedia, why don't we get the same behavior? And in this case, I feel like this is the simplest possible example where the scale is not removable. There is a fundamental scale, delta x, for the separation between jumps, and a scale for the velocity, which is the motion of the particles. And we can take limits to get a differential equation, but that doesn't mean that it's going to be good enough. We certainly have gotten used to this in quantum field theory in places where, like with Wilson's work in the renormalization group, the scale is important in some ways. There are ways in which it can be removed, and I'm going to show this is a case where it doesn't. The scale does not just disappear. And if you do cause it to disappear, you introduce an error, and that's what gives you infinite propagation. So, but PDEs are really important to us, so we would like to use PDEs. They are the backbone of many of our mathematical methods and the way we converse about things. So here I've just set up my little grid, number of particles at each location, x, and I simply, that's really that's really all there is to say. It's really very, very basic. You can do a differential equation expansion of it, and you can you sit there and suffer with it and the coefficients and find a time derivative for the end result, force it all in. You can look over the paper if you want, but there's not really that much to it. And at the end, you get this infinite order expansion, like in number 7. Infinite order, it's very annoying. If you cut it off at the beginning, wow, you've got Fick's law. But the point is, these extra terms are essential in restoring the causality, and they're not going away. You could try to throw in the next term and do a better job. And of course, the tails on these distributions are small, so that's not necessarily a terrible idea. I did notice that this could be rewritten as an operator on line 10. So there's this funky operator, which is the hyperbolic secant of that delta x partial x operator, -1, over U. And of course, that really is just giving me what I see in 7. These things show up with finite difference equations. If you study finite difference equations, you'll find trig functions popping up. So it's not really a very there's not a lot that really needs to be said here, and it's too bad that so much has been said, because it really does resolve very, very nicely and very quickly if you just do a direct solution. And the conclusion is just what people don't want to hear, is that the PDEs don't work. They don't work to that level of accuracy. You're not going to force a PDE jacket on this system. I did go out of my way to make a little discussion here over like how to talk about currents. And then there is a higher dimensional generalization of this. I care a lot about this because I'm very interested in how waves and flows and diffusion interact with each other and the consequences of this. So I'm really not going to belabor this. I feel like that point is simple. What's going to follow, though, in the following videos are going to be much more interesting conclusions. First of all, hydrodynamics. This problem is all through hydrodynamics. For example, I could take, like let's say I just take a rod in a viscous fluid and I start to turn it. How fast does the drag propagate out to infinity? Well, it's at infinite speed. You still have the same problem, and the resolution is still the same. Is that in viscous hydro, you're going to need something like this. You're not going to really get away with partial differential equations. You're still going to need to retain something about the microscopic scale and features of the system, something akin to a finite difference equation. But it gets much more interesting. And this is going to be a recurring topic of these talks, is when do the standard methods fail us? And when it comes to acoustics and ocean waves, you're going to find some cases where they fail really dramatically. So stay tuned, and I will see you in the next video.